This video is going to be the background information that you're going to need to know for the first week of the lab we're going to do on acids and bases. It's important to know that acids and bases all operate in water. So before we talk about them, we're going to talk a little bit about water. So here's a water molecule. Now what can happen is that random changes in the electrical field around the water molecule can cause it to break up on its own. The term we have for this is autoionize. This doesn't happen very often. About 1 in every 600 million water molecules will do this. So what happens is one of the hydrogens breaks off, and what you're left with is a proton. So H plus is just simply a bare proton. And the other ion you're left with is OH minus, which we call hydroxide. So we can represent this with a chemical equation. And this actually goes back and forth. So we use an equilibrium arrow right here. So we have water breaking up into the two ions. It's aqueous, it's all in water. So that's what pure water does. Pure water breaks up into ions on its own. So it forms a proton and it forms hydroxide. But that's not really the most accurate way to represent that, because when you have a proton in water, it doesn't just float around on its own. Another water molecule will take it. So here's another water molecule taking the hydrogen ion, otherwise known as the proton. And so what we get is a bigger ion here. This ion, which is water having 3 hydrogens, is known as hydronium. So a more realistic depiction of what's happening is the hydrogen goes from one water molecule to another. So what we get is hydroxide and hydronium. So another way to represent that, and this is a little bit more accurate, is we have 2 water molecules and we end up with H3O plus, hydronium, and hydroxide. So when we talk about H plus as a proton, we can use that interchangeably with this other ion, hydronium. So you'll hear this talked about interchangeably. A proton, we're going to say, is the same thing as hydronium. Hydronium is a little bit more accurate because in water, you don't just have bare protons floating around. A water molecule will come along and take it for itself. So hydronium is a little bit more accurate, but we do use the word proton to describe this ion. All right, so let's talk about actual amounts here. So at about room temperature, the concentration of these 2 ions is a pretty low number, 1 times 10 to the minus 7 moles per liter. So we can set up an equilibrium constant for this. So we have 2 products here, so they're going to go in the numerator. And on the denominator, we have water. Water is the solvent in this case, and solvents are excluded from the equilibrium constant expression. So what we end up with is just the numerator. Now if we plug these numbers in, there and there, and we multiply them, we get 1 times 10 to the minus 14. That's the equilibrium constant from water. And what that's saying is that at equilibrium, we don't have very many of our products present. That's what that is saying. Okay, now we're going to start to talk about acids and bases. Let's say we have an acid and we add it to water. So at the beginning, we have our concentrations of H plus and OH minus that we talked about earlier. We have our K value. And let's see what happens to these concentrations when we add the acid to water. So after, we end up with a concentration of H plus at 0.1 moles per liter. That's higher. And the concentration of OH minus ends up at 1 times 10 to the minus 13. So that's now lower. But if we multiply those numbers together again, like we did earlier, what we end up with is the same value, 1 times 10 to the minus 14. And that happens because the concentration of H plus goes up, the concentration of OH minus goes down, and they multiply and end up being the same number again. So that ends up being the same. So one of the definitions of what an acid is a substance that causes the concentration of H plus to go up and the concentration of OH minus to go down in water. All right, let's talk about bases. So we're going to start off with the same situation that we had earlier. And let's say we throw a base into water and we measure the concentration afterwards. So afterwards, we have a concentration of H plus that's lower. we end up with a concentration of OH minus that's now higher. But just like before, if we take these two numbers and multiply them, you end up with the same number again. So they're the same. Now, another definition of what a base is a substance that makes the concentration of H plus go down in water and the concentration of OH minus go up in water. That's one of the ways we can define a base. All right, so here is a table that summarizes all those numbers, all those concentrations we looked at. Now what you notice about them is that they tend to be pretty small numbers, and also they tend to vary by many orders of magnitude. Like this is 0.1, this is 10 to the minus 14. So we can clean these numbers up. We can make them into nicer numbers that takes this huge range and squishes it down. So the way we can do that is by taking the base 10 logarithm, and when you do that, what you end up with is these numbers turn into this. So those numbers are a lot more manageable. Something else we have here now is a negative sign. So the way we can get rid of that is by multiplying it by -1. So if we multiply those by -1, the negative sign goes away. So when you take the logarithm of something and you multiply it by -1, the mathematical symbol we use to represent that is lowercase p. So we put p next to these ions, and what you end up with is pH. That's where pH comes from. It's the negative log of the concentration of H+. But that's not the only thing we can take the logarithm times -1 of. We can do that for the hydroxide ion, and when we do that, we get POH. We can also do it for the equilibrium constant, and we get pK. All right, so that's where pH comes from. It's -1 times the logarithm of concentration of H+. So there's something to notice about pH and POH and pK. They relate to each other in a certain way. If you take these two and you add them together, for all three of them, 7 plus 7, 1 plus 13, 12 plus 2, you get 14 every time. So we can get an equation out of this. And basically says that pH plus POH is always equal to 14. The reason that's useful is, let's say you measure the pH of a solution. You'll know that pH plus POH equals 14, so if you know what pH is, you can easily calculate POH. All right, so the pH, which is what we usually talk about when we're talking about acids and bases. POH does come up sometimes, but it's pH is predominantly what we talk about. It can have a number, and this number is all about extremes. So in the middle, we have 7. A pH of 7 means that these two ions are balanced. So we say that the solution is neutral. Neither one of them is present in a higher amount than the other. When you get less than 7, so when pH gets lower, you are in what we call acidic territory. And in that side, there are more hydrogen ions than there are hydroxide ions. So anything with a pH less than 7, this will be the case for. When it's above 7, we say that the solution is basic, and the opposite is true. The seesaw tips the other way. Now we have more hydroxide ions present than hydrogen ions. So the pH tells you about the balance of the ions. And the way the math works is, as the pH gets lower and lower and lower, the amount of hydrogen ions gets higher and higher and higher. And as the pH gets bigger, the amount of hydroxide ions gets higher and higher and higher. Another thing that's going to be important to do is to go backwards, to take a pH and convert it back into concentration. So here's how you do that. The way you get the concentration of H+ is you take 10 and its exponent becomes pH, becomes the pH with a negative sign in front of it. So if the pH was 3 and you're trying to find the concentration of H+, it would be 10 raised to the power of -3. By the same hand, if you're trying to find the concentration of OH-, you just take 10 and you raise it to the power of negative POH. That becomes the exponent. All right, there is another way to define what an acid is. So to define that, we're going to look at a chemical equation of an acid being an acid. So the way we're going to abbreviate an acid is HA. That's going to represent our acid. So HA, this acid, is going to interact with water. So what it does is it's got this H, it's got a proton, and it donates it to water. After it donates it to water, we get this ion, which is the acid after it lost its proton, and hydronium. So another way to define what an acid is it's a proton donor. It has a proton that it gives away. So in order to be an acid, you have to have a proton to give away. Now the reaction that we've shown here, where the acid is reacting with water, we call that hydrolysis. So think of water. When you see hydrolysis, just it has water implied in there, and that's exactly what's going on. It's reacting with water. Now acids are not all created equal. Some are very good at giving their proton away, some are not. The ones that are very good at giving their proton away we call strong acids. And by that we mean that 100% of the acid will donate its proton. And because of that, the reaction is not at equilibrium. It only goes from the left to the right, and that's it. An acid that's considered weak gives its proton away about 1% or even less of the time. So that's significantly less. And this can get much less than 1% as well. So in that case, it can donate its proton, but it can also take it back. So we use the equilibrium arrow when we're working with a weak acid. So the question is, how do you know if an acid is strong or weak? Well, the way you know that is the list of strong acids is relatively short. So if something isn't on this list, then it's considered weak. So we have a list of acids here that you should commit to memory. These are good to know. It's not a very long list. And the importance of that is that if you know that an acid is not on this list, you can say that it's probably not a strong acid. Okay, so the definition of an acid is a proton donor. Now we're going to talk about bases. Base is going to be represented with the letter B in this chemical equation that you're going to see in a second. So just like before, it's going to react with water, only now what's going to happen is essentially the opposite. Rather than giving a proton away, it's going to remove a proton from water. So then what we end up with is the base with a proton, so it's BH+, and water after it lost a proton, hydroxide. So another way to define what a base is it's a proton acceptor. It takes in the proton. So it's essentially the opposite of an acid. So bases also are strong and weak. Strong bases will accept a proton 100% of the time, and the reaction only goes from the left to the right. We say that the reaction goes to completion. Bases can also be weak. Just like with acids, it's a 1% or less. 1% or less will accept a proton, and we use an equilibrium arrow. The way you tell if you have a strong base is if you have hydroxide attached to one of the elements that is on the first two groups on the periodic table. So for example, if we have sodium with hydroxide, so sodium hydroxide is considered a strong base. Magnesium hydroxide is another strong base, and so on. So that pattern continues for these elements in general. Okay, now what's important to notice is that when you have a weak acid, the acid loses its proton, turns into that, but it can also take it back. And that's what makes it weak, is the fact that it can take its proton back. So we have this equilibrium arrow here when something is weak. That means that the reaction can go backwards. So what we're going to focus on next is the reaction going from the right to the left. All right, so let's ignore these other substances so we can focus on this and this. This used to be the acid. This is the acid after it lost its proton. And if you look at what it does, going from here to here, it gains a proton. So that is acting like a base. So what the acid used to be is actually acting like a base. So we have a specific name for this kind of a compound. We call it the conjugate base. Conjugate in this context means kind of like a twin. So every weak acid is going to have what we call a conjugate base. Okay, so a weak acid has a conjugate base. Now strong acids don't go both ways, so they by definition can't have a conjugate because you have to go backwards in order to be able to gain the proton back. All right, so for weak bases, when they're weak, they go both directions. So just like before, we're going to look at the reaction going backwards. We have BH plus, and then we have B. So that means that the substance here is losing a proton. It's donating it. And we call that an acid. So going backwards, it's acting like an acid. It's going from BH to B. So the name for this is the conjugate acid of this weak base. So every weak base is going to have a conjugate acid associated with it. All right, so that's about it. When you get into lab, you're going to be looking at a few things, how strong acids and bases are and ranking them. You're going to be looking at acids and bases and their conjugates. And then finally, you're going to be looking at the strength of an acid or base and how strong its conjugate is. Is there a relationship between how strong the acid is and how strong its conjugate base is? And then the same thing for bases. I will see you in lab.